Alright guys, in this video we've been talking about polynomial functions up until now, especially their behavior of their graphs and what those look like and their rules. We're really going to start to analyze these functions with respect to their zeros and then their turning behavior here. And so when we look at this, we're going to start with what we mean by a zero of a polynomial function and how many must exist. So notice that it says it can be shown that for a polynomial function of degree n, the following statements are true. And so if we have a polynomial of degree n, sorry, let me fix this here, degree n, then we can say that the number of zeros is at most n real zeros. And so one thing we want to acknowledge going forward is this: whatever the degree of the polynomial is, that is the most number of real zeros that we can achieve or obtain from it. Now with respect to number of turns, okay, or turning points, these are spots on our graph where it goes from decreasing to increasing or increasing to decreasing. So we've heard these called relative minima or maximum. But what we can say is if the degree is n, then we will say that it has at most n minus 1 turning points. Okay, so important to know as we continue to analyze these graphs for their zeros and their behaviors here. With respect to zeros, what do we want to note about these? Well, with respect to zeros, what we want to acknowledge is, first of all, that all four of these statements down here mean the same thing. So when f is a polynomial function and a is a real number, the following statements are considered to be equivalent. We say that x equals a is a zero of the function. And that might be the truth, but one thing that I can tell you is a zero of a function is any x value that when we plug it in, we get 0. And so I would write down these four statements here, but next to the first one, what we're basically going to want to write is this. This implies then that if we plug a into this function, we're going to be at a height of 0. Okay? Another way to say this is to say that x equals a is a solution of the polynomial equation f of x equals 0. And so kind of like what we just wrote right here, if we plug a into this function here, then this statement would be true because we would say that this is some x value that when we plug it in, we get a function value or a height of 0. Okay. Now, these last two, I'd say number 4 here makes probably the better sense, but we're saying that when we plug in a, we get 0. So if that's the case, a comma 0 is on the graph, we can acknowledge that the zeros of a polynomial function occur at the x-intercepts of the graph of our function. So all zeros of a function, if it is some polynomial function here, have to occur at x-intercepts. And then last but not least, we say x minus a is a factor of the polynomial function f of x. And so basically what I want to acknowledge here is this: if x equals a is a solution, then if we set this back equal to 0 again, it would imply that x minus a had to be one of the factors of our polynomial function, since we would have had to have set that factor x minus a equal to 0 to obtain the solution x equals a in the first place. So what we are going to work on then here is to kind of search for some zeros of this polynomial function and also kind of determine what we can about its graph. So it says, do us a favor, find all real zeros of this function, then determine the maximum possible number of turning points of the graph of the function. So what I actually want to start with is this. First of all, this function is already written in standard form. So our exponents go in decreasing order, and we're able to easily determine the leading coefficient and the degree. So our leading coefficient here, let's go and identify this, is -2. Our degree, okay, is 4. So now that we have these in our back pocket, let's go ahead and write a few things that we can determine here. There will be at most 4 real zeros for this function because our degree is 4. And likewise, we can say there will be at most 4 minus 1 or 3 turning points. Maximum or minimum points. So we know this kind of going in. As a matter of fact, we could even comment on the end behavior of this graph, which even though it didn't ask, we're going to write it anyways. We know with respect to end behavior, we use the leading coefficient test. And so the leading coefficient test, the leading coefficient specifically tells us how the right-hand side of the graph will behave. And so in this case, because the leading coefficient is negative, the right side has to fall. And also because our degree is 4 or even, the left side would also have to fall here. So now to get to the task at hand, let's find the zeros of this function. Remember, zeros are the x values that cause our y value to be 0. So if we're going to search for zeros, the very first thing we do is we substitute a 0 in for our y value or our f of x value, and then we go and search for its zeros. Now here's the rule. If you can, let's get x by itself, but most of the other times, if there are x's to various powers with polynomials, we're going to be stuck factoring. And so it is important, that we know about this thing called the zero product property. And this basically states that given a product of factors like a times b, if the product is 0, then two conclusions could be drawn. Either a was 0 or b was equal to 0 here. And so our goal with factoring is to be able to write it as the product of a bunch of factors coming out to be 0, so we can set our individual factors individually equal to 0. So with this, let's try to factor it, starting with the GCF first. I noticed that they both have in common a 2 and x squared. So just to kind of get our leading term to be of a positive nature, not that we have to, I'm going to go ahead and factor out a -2 with my x squared here. And we're going to write this as, well, our first term would be just a plain positive x squared left over, and our second term we'd have to write a -1 to take the place of this 2x squared that existed there. I also notice that this right here has 2 terms, and it is a difference of 2 squares. So we're going to continue to factor this as much as we possibly can, and so we get these conjugate factors here. So looking at these two factors, I notice they both have 2 terms, but respectively each of these, okay, let's put it this way, are neither of them are differences of squares, and so we're kind of stuck with what we have right here. So in this case I have 3 factors, kind of like this here, and so what we're going to see is that I can set now each of my individual factors equal to 0 and solve them. And so looking at these 2 factors on the right, they are my favorite just because we kind of said on this other page here, if x minus a is a factor of the polynomial, then x equals positive a is a solution. And the reason why we say that now is just because if x minus 1 is our factor, then x equals 1 must be our solution here. These are kind of saying the same thing but different ways. In this case we get -1, and then in this case over here we'd have to divide first by our -2, which really isn't going to matter. And then we're going to have to take the square root of this 0 right here, which leads us to an interesting solution. We get +0 and -0. And so I know 0 is a neutral number, but you're going to see that I have listed it twice. And the reason why is because I really want to emphasize the fact that we got 4 total zeros. And because the degree of this function is 4, we should have expected at most 4 zeros. And so the last thing I want to do is I actually want to go look like. And so we're going to go graph this in Desmos, -2x to the 4th plus 2x squared. Let me get all this out of the way. So we're going to say f of x equals -2x to the 4th plus 2x squared. And so some things I see. First things first, I can tell that the left-hand side and the right-hand side have the same behaviors. They both fall. And that our right-hand side had to decrease because of our negative leading coefficient. The other thing is turning points. I see that it goes from increasing to decreasing here. So that's 1 turning point, 2 turning points, and then 3 turning points there. If our degree was 4, then we should have expected at most 3 turning points. And then last but not least, we look at our zeros here. We have -1 and +1, and we have 0. So in terms of how this graph behaves at these different x-intercepts, we had 4 solutions. So why am I only seeing 3 x-intercepts? What I want you to notice is that it turns around at 0, 0. It doesn't cross the x-axis. It just touches and turns back the way it came. Whereas at -1 and +1, our graph goes from having negative y values to positive y values, or positive to negative. It crosses the x-axis there. And so why does this happen? Why does it happen that it crosses at -1 and +1, but it doesn't cross at 0? Why does this happen? And in large part, whoa, this thing's misbehaving here. Sorry, guys. Hopefully this doesn't keep up. There we go. Let's try again. Oh, it's one to act up. I apologize. It has to do with the number of zeros that we obtained here. And so what I want to make sure that we write here is that we got the same 0 twice, which is an even number of times to have gotten this 0. And on these here, we got each of these zeros once. So each of these zeros once. which is an odd number of times to have gotten those zeros. So what we're going to look at next then is what we refer to as the multiplicity of each zero, or what happens at repeated zeros. Okay, so when we talk about a repeated zero, we're saying that maybe this is a function that has a factor x minus a, but it has it more than one time. Maybe it has it 2 or 3 or 4 times. But if that's the case, it's going to it's going to yield what we call a repeated zero, x equals a, of a multiplicity of k. And so when we talk about what is k here and how does it have to do with the multiplicity, if we want to write a definition here, the multiplicity is the number of times a zero is obtained, a zero or a solution is obtained. And so what I want to kind of look at is, well, what's true if we get the same zero an even number of times versus an odd number of times? So you'll notice that I'm going to want to have you write these both down. But let's look at what happens when I get the same answer an odd number of times versus what happens when I get the same answer an even number of times. And hopefully we can get our graph to work here without spazzing out. So what I'm going to do is I'm going to build a function here, f of x, and what I'm going to say is it equals x minus 2. Why not? Maybe my factor is x minus 2, and maybe that's the only factor in this expression. So if I were to set this equal to 0 and solve it, I would get positive 2 as my only solution. And you'll notice that we got positive 2 for an answer only one time. So now, what happens when I take this x minus 2 and I make it a factor twice? Let's try something here. If I make x minus 2 a factor twice, x minus 2 twice, there we go. You're going to notice that it does indeed hit at x equals 2, but this time it doesn't cross the x-axis. It just kind of touches and turns around there. Okay, so what if we make this a factor 3 times, put in another x minus 2? It still crosses at x equals positive 2. It's just that it crosses this time, whereas if I make this a factor 4 times, now it touches and turns around again. So in general, what you're seeing with what I'm going to have you write down on that other page is that we're saying in general, if I raise this to the kth power, and I say k is some number between, I don't know, let's do this. We'll go from 1 to 10, and we'll go by steps of 1. You will see that if I get the same answer an odd number of times, once, 3 times, 5 times, 7 times, it means that that's going to be an x-intercept of our graph, but it has to cross at that 0. Whereas if we get the same number of 0 an even number of times, maybe like 6 times, or 4 times, or twice, anytime we get a same 0 an even number of times, then it's going to mean that it's going to touch but not cross. It's going to turn around. So when we look at this here, let's see if I can get this working again. That's okay. It says that when k is odd, when we get the same 0 an odd number of times, the graph is going to cross the x-axis at x equals a. But when k is even, the graph touches the x-axis and turns around but does not cross the x-axis at x equals a. So what we're going to do next then is kind of just take a look at this graph right here with respect to its zeros, and then we're going to work on making a sketch.